All right, so I've already explained to you how VASCO works in general and that it stores procedure summaries not symbolically, but using concrete input and output mappings. And we also talked a little bit about this context transition diagram and using an extended example that uses constant propagation and pointer analysis both together. I want to show you why this is useful. And here I'm going to be using a C-like language because using C you can do interesting pointer mumbo jumbo, which would be hard to express in a Java-like language, but it actually makes for a more concise example. So let's take a look at this. So here we are still having a similar program to what we had before. We are initializing A and B to these two values. But now we are initializing also two pointer variables. So now after this statement, P is pointing to the memory location of A, and Q is pointing to the memory location of B. Okay. Then we are calling foo, and foo is reading the values out of these memory locations again. So it's copying them into X and Y. They're being added, so it's the same addition that we had earlier that will yield 5, right? And the value is being printed. But now the evil bit is starting. Now this is actually after adding these pointers together, it's actually swapping the global pointers around, right? So now after that, Q will point to whatever P was pointing to, and the other way around. That is evil to some extent because then we are calling foo again. So this time we will be accessing the same values but actually the other way around. Okay, so X will then in the second call read the value of B and Y will read the value of A, which fortunately to the addition it doesn't matter, right? Because this is commutative. So also in the second call, the value of Z will definitely be 5. And we actually want to determine that Z is always 5. But in order to do that, we really need to know about these pointers and whether they are swapped or not, and in particular, what they look like at each particular calling context. So that's what makes this example really interesting from a program analysis point of view. So let's get our hands dirty a little bit. Let's first compute a pointer analysis because that's really going to be necessary in order to be able to track these constants. So we are starting a pointer analysis in some initial context that we call x0. And initially we know nothing about any pointers. Then we learn that P is pointing to A, and then later also that Q is pointing to B. Okay? Then we are processing the call to foo, so we are actually creating a new context, x1, that is initialized as you see here. And again, we assume that all of these variables are global variables. And yeah, that stays the same until in the end here, these two values are actually flipped, right? So here now P points to B and Q points to A. And then we also have a second calling context down here, which is context x2, that is called at c2, which looks exactly the same as the first one, except that now here all these values are flipped, right? So here we are starting with this mapping that maps P to B, or that where P points to B and Q points to A. And then this is being reversed again to arrive at the environment that we had at the very beginning. Okay. Now, if you then do this, you will basically in the caller and main get this pointer information here, right? So we now have learned that we have this mapping here, this flip mapping after the first call to foo, and we arrive at the original one after the second call to foo. The important point now, and that's really the most important point about this example, is that we now must not merge pointer information when doing the constant propagation. So the pointer information for these different calling contexts, C1 and C2, it must be treated separately, and we must identify the right pointer assignment here for the right calling context. Otherwise, this is not going to work. Otherwise, we're going to lose precision. So that you believe me, let me show you what were to happen if we did merge. So assume that for a minute. If we did merge, then essentially at the beginning of the analysis of foo, we would be getting this analysis information, right? So we would be saying, well, we know that P can point to A or to B, but we don't really know which one. And the same is true for Q. But this now gives us a lot of trouble because now, well, X can either point to 2 or 3, and the same is true for Y actually. So this is not constant anymore, right? And therefore also Z would be determined to be not constant. We could only bump it to top, we could only widen it, and then we get imprecise analysis information. So the idea and the solution to this problem is now to keep these contexts apart. So we want to correlate the contexts that we compute for the constant propagation with contexts that we have previously computed during the pointer analysis. And this is exactly where this context transition diagram comes in handy, because we can use the call sites that are encoded in that diagram to make that correlation. So again, the same program as before, but now we assume that we have already computed the pointer information, so already have that context transition diagrams for these contexts here. And remember that x0 and x1 and x2, they are contexts with respect to the pointer analysis. Okay, so they tell us about input and output values in the pointer analysis. Now I'm opening a new context, y0, which is a context for constant propagation in the main method. Okay. And at the beginning, we assume nothing is constant, then we learn that A is 2 and that B is 3 and so on. The pointer assignments don't really matter to us, and then we get to call site C1. And now we are opening a new calling context, Y1, for foo. Okay. And now it becomes interesting. So we know that Y0 is a context for method main. Okay. We also know that we are now processing call site C1. And looking at this context transition diagram, we know that we already have pointer information also for procedure main, which is encoded here in x0. And we know that using the same call site C1, okay, we get to x1, to this particular pointer analysis context. And because of this, we know that this is the right initial pointer information that we need to deal with when analyzing foo under that particular context y1. Okay? So using this call site matching here, we can draw up that information. We can make use of it. And now this is really nice, right? Because now we have this pointer mapping. We now know that x now has the value 2 and y has the value 3 because we can resolve that pointer relationship here. And we now know that z precisely has the value 5. Then we do the same again for call site C2. For call site C2, we now know that we need to take a look at the context x2, which looks like this, right? So it has the flipped pointer assignment here. And again, we can determine the very same precise information. Now we have to recompute the constant propagation for foo in this case, right? We have to do that because part of the context information is different, right? In particular, the pointer information is different. And therefore, because that matters here, it needs to be recomputed, but we do get a precise result, right? Now, for both calling contexts, we learned that z has the value 5 here at this print statement. Okay. And that's our final result then, right? So we basically have now obtained that information. And now we can take a look again at these context transition diagrams and these tables that I showed you earlier. So basically, for the points to analysis, the table is as you would expect, right? So you have these different entries, one for main and two for foo, with these different entries and the swapped exits that we have computed. What's interesting to look at now is the table that we have for constant propagation, because now here you have these somewhat strangely looking entries for the procedure column. Now, what does this mean? So this is really telling us here that we are analyzing the procedure main using a constant propagation, but assuming context x0 for the pointer analysis, okay? So that's sort of specializing the procedure. It's basically saying, I'm looking at a special variant of the procedure where I'm already assuming exactly these pointer mappings here. Actually, it's not right. It's these pointer mappings, right? I need to look at the entry node. Okay. But then here I am analyzing foo under the context x1. Okay. And that now tells me that I'm analyzing foo under this initial pointer mapping here that I have computed. Okay. And that then allows me to precisely determine these values here. And yeah, that's that. So in VASCO, using context transition diagrams, one can correlate multiple different and subsequent analysis with one another. Okay. So they need to be subsequent in the sense that, well, as you saw here, when I'm conducting the constant propagation for a certain procedure, then for that same procedure, I need to have pointer information already, right? So at the very least, for the same procedure, that needs to have been computed already. One analysis can then analyze a procedure under the context of another. We just saw that, right? So we were conducting constant propagation using these sort of specialized instantiated methods that were using information from the pointer analysis. And as I also showed you, this can then yield more precision than using the naive way in which you would merge overall contexts before actually accessing the previous analysis information. And in general, such correlation of context, it's really important whenever you're using, whenever one context-sensitive analysis is making use of information from another context-sensitive analysis, right? So here, in the example, we had this client analysis that's a constant propagation that uses a pointer analysis. And it's very often the case that you have one analysis that is using a pointer analysis, but there can even be other kinds of analysis. So for instance, I don't know, a constant propagation could benefit, for instance, from a liveness analysis, right? So you might have pre-computed that already, and then you could make use of that. And but then it is important that you correlate these contexts like I showed you, because otherwise, otherwise you would still maybe get a sound result, but you would get one that is unnecessarily imprecise. And you can and must also correlate contexts in other frameworks, not just in VASCO. So we will also be looking at frameworks such as IFDS and IDE. I will be explaining these in the next few lectures. And there we will see that also their context correlation is really important in these cases where you combine multiple of these analyses together. We will be talking about this very excessively actually in DECA II, where we talk about some more real-world analyses and how they are constructed. And they make heavy use of this context correlation. And there I will also be discussing different flavors of how to do that. So I've actually just shown you how you can correlate different analyses with one another using these context transition diagrams, and that really makes well, for a very nice versatile approach. But nonetheless, VASCO actually does have some drawbacks that I also want to highlight, and in particular, it gives you not always optimally efficient solution for problems that actually are distributive. So let's take a look at this example program here. We again have a main procedure that is calling this procedure foo, which is doing some computations here. But actually, it's doing these computations only on the input value h, the first parameter, which is then propagated to j and then to k and then returned. So the value h in particular then is relevant for the procedure summary for foo, whereas the parameter I is simply printed. So that doesn't really have any effect on the caller, and therefore it also doesn't need to become part of any procedure summary. Okay. Also note that the constant propagation here, it can be linear, so these are only linear equations. That means they only basically refer to a single variable, not two of them. And therefore, this is actually a problem that fits into a distributive framework. Now, if we were to apply VASCO to this as a constant propagation, we would get the following. So we would start analyzing the procedure main in context x0, which starts with an empty set of constants here. And then in context at cos at c1, we would enter context x1 at foo. And we basically would get this mapping. So here A maps to 1 and B maps to 2. And because of this parameter assignment, we basically have the mapping h maps to 1 and I maps to 2. And then we have this computation being done, which actually in the end leads to k getting the value 3. And this is returned, so it becomes the new value of c here. And now that means at call site c2, we are forming a new context where this variable I now has no longer value 2, but now it has actually inherited this value 3 that k had originally, right? So we have this new input context here. And that is now causing a bit of a problem because, like I explained earlier, the value of I has no bearing whatsoever on the summary of foo because, well, it has no bearing on the caller, right? It's being printed here, okay, fair enough, but that's about it. But nonetheless, VASCO has no way of figuring this out, right? So it sees that there's a new input environment here for a variable I, and now it needs to go through this whole computation again, which makes it relatively inefficient, right? So we need to look at every single statement again. We need to compute all of these different flow functions again, only to then figure out that in the end we basically have an identical summary, right? It's not quite identical because here we do have different exit values for I, but as I told you earlier, typically these local variable values, they are projected away in the summary, right? So they are not useful for the caller, so they would not even need to be part of this table in essence. And then if you only look at these other entries here, they are identical, and therefore we have really wasted work, right? So this only differs in values for I, and the difference does not matter to foo, but nevertheless we are reanalyzing all of foo, including what needs to be done for h, right? And that is suboptimal, and as I will show you later, approaches such as IFDS and IDE, they actually allow you to deal with these cases more efficiently. So that should tell you when you have a distributive problem, it might be preferable nonetheless to use a framework different from IFDS, different from VASCO, excuse me, because otherwise you can get these inefficiencies. So just to recap, the VASCO frameworks allows one to use tabulation or memorization of input and output pairs. And yes, this does eliminate the problem of analyzing equivalent contexts repeatedly, as you have seen it in the call strings approach. However, for a summary to match and to be reused, contexts must really be identical. And in the example I showed you, they were not identical, right? So we had this variable I that had a different value for both contexts, and that then led to a reanalysis of the Corley procedures. And yeah, in general, this property hinders reuse in cases in which contexts could actually be considered equivalent for all purposes of the Corley, but in which they are not really the same, right? So they might be equivalent, but they are not identical. But VASCO doesn't have any notion of equivalence, right? It can only tell whether a context is identical, and then it gives you reuse, and for non-identical contexts, it doesn't. But as we will see, many distributive problems, they have this property, right? So often they have contexts that can be considered equivalent, although they are not identical. And then you really want to have this, more liberal form of reuse that VASCO cannot really give you. But we'll be talking about this in the next 2 weeks. I'll be talking to you then. Bye-bye.